Another interesting thing that comes up when you look at applications of this sort is eigenvalues and eigenfunctions. So suppose we desire to solve y double prime plus c times y equals 0 with boundary values y of 0 is 0 and y of l is 0. See, I don't have a derivative. I have a value of y at two different points. So what do you suspect we would do here?
I really don't know.
Well, case 1, if c is 0, then y double prime is 0, and the differential equation is a differential equation, and of course this would be a function whose second derivative is 0, and this is the function this is the first derivative of that function, and y of 0 equals 0 forces b to 0, and y of l equals 0 means a times l plus 0 equals 0, so a equals 0, and we only have the trivial solution y equals 0. If c happens to be a negative number from the characteristic equation m squared plus c equals 0 with c less than 0, we get the solution y equals a times e to the negative square root of ct plus b times e to the negative of negative square root of ct. Remember, c is a negative number, so what's under the radical here and here are positive. Now, from the boundary condition y is 0 equals 0, we get a plus b equals 0, see? If this is 0, when this is 0 and this is 0, then a plus b is 0. So b equals negative a. And from y of l equals 0, we get 0 equals a times e to the negative cl, e to the square root negative cl, plus b times e to the negative of square root of negative cl. And substituting what we know about a back into that, guess what? We get 2a times the sinh of negative square root of c times l. That's what this really is. And since l is positive and c is negative, 2a times sinh of negative square root of cl equals 0. And that forces a to be equal to 0, which is negative b. So again, we got only the trivial solution y equals 0. Oh, that's not a problem, because case 3 is the interesting case. Here, our c is a positive number, and our characteristic equation has roots plus or minus square root of ci. So y equals a times sine of square root of cx plus b times cosine of square root of cx. So y of 0 equals 0 forces b to be 0. And y of l equals 0 means that a times the sine of square root of cl equals 0. Well, that's a different ball game. Because, of course, a could be 0, but that's not our only choice. Because it could be that sine of square root of cl is equal to 0. And when would that happen? That would happen if the square root of cl is n times pi for some value of n. Well, solving this for c, I guess I'd divide both sides by l and then square both sides. So c equals n times pi over l squared for n different values of, actually any old natural number. So that makes y equal to a sine of square root of cx a solution for any a if c equals pi squared over l squared, 4 pi over l squared, 9 pi over l squared. You can probably see how this happens, 16 pi over l squared. And these values, pi squared over l squared, 4 pi squared over l squared, etc., are called characteristic values or eigenvalues for the function y double prime plus cy equals 0. And the corresponding function, see, once we know what c is, then the corresponding functions, y equals a times the sine of n pi over l, are called characteristic functions or eigenfunctions for y double prime plus cy equals 0.